to go over like all the basics. So yeah, this is Math 491. And I don't know what to call it, but I guess chaos, a survey course on chaos or something. I'll just call it chaos.
Yeah, chaos. Keep it simple.
If we want to call it anything else, we can call it something else.
Course starts and chaos ensues, yes.
Okay, so we're going to be talking about chaos, and we'll have a very very casual class, contrary to what my attire might suggest. But I mean, I want you guys to give as much input as you can, and we're all going to kind of learn together about various things. So the first lecture that we're going to do, before that, I guess I should go over the syllabus.
Has everybody here taken 473 or 573?
No, not everyone.
Not everyone, okay.
So yeah, I'll review with them some of the basics from 473. So I guess you all got the syllabus. I did say you should know linear algebra, differential equations, so we'll go over some of that today, and if there are some topics that you're perhaps rusty on, you should kind of go over that stuff. You should be able to use p-plane and d-field for certain things, but that's really easy. I can show you how to do that. It's a good idea to be able to use ODE 4.5. I mean, you can come up with your own solvers, but since ODE 4.5 is already there, you might as well use that for some of the numerical homeworks.
What is that these times? Rungakuta?
It's Rungakuta, yeah. So it's Rungakuta 4 and Rungakuta 5, and using those. So yeah, know how to use that. If anyone doesn't, I'll send some sample code. And you can very easily learn how to use ODE 4.5. There isn't much coding to it.
ODE 4.5 is just a built-in function in
Yeah,
MATLAB, right?
It's a built-in function in MATLAB, yeah. So it should be really easy to use that. We will have homework and quizzes, but quizzes will be easy. So next week, well, no, I'll make it fairly simple. Homeworks, on the other hand, I do want to kind of make interesting. So we'll have a quiz next week on like basic linear algebra and differential equations, just to see that you know it. So be prepared for that. So lectures on the syllabus are organized in 1-hour groups. So since we're having a 2-hour class, we'll have 2 of these lectures per week. So first we're going to just do some reviews, and then we're going to do some more interesting things. We might take out some things, so this is subject to change. We might move around some things. And we also want to do 4 experiments plus a little field trip to the Math Bio lab to look at their experiments. So the 2 experiments that we already have material for are the chaotic scattering experiment and the BZ reaction. So we already have the chemicals and all that for the BZ reaction, and chaotic scattering, I have all that stuff anyway. So the other 2 are going to be Chua's circuit and the double pendulum. The double pendulum is probably going to be the hardest to do. I don't know if we're going to be able to do that, but hopefully we can. Yeah. So hopefully we can do that.
It might be a virtual pendulum.
Yeah, exactly. Yeah, we might just do like a numerical experiment with that. But for the Chua circuit, I guess Ian might be the only electrical engineering person here. So
I brought a breadboard.
Okay, well we have breadboards too, so we can just go through the equipment and then see what we need.
Okay.
And hopefully we have everything. We should have most things. We have oscilloscope, so if we need to buy something, I guess we could just buy it. So we should be able to do 3 out of 4. Definitely 2 out of 4. Hopefully 3 out of 4. And if we can get someone to make a double pendulum, then we can do all of them.
Searching for magic pendulum.
Yeah, exactly. So that's basically what I want to kind of give you out of this class to kind of see what chaos is in a physical sense, to kind of help you develop that intuition of what chaos is. But before we can do that, we have to make sure we know the basics. So let me write down all the topics that we should know from ODEs and linear algebra, and you could kind of throw in some topics if you think some more are needed. So for ODEs, I'm thinking, well, you should know how to sketch direction fields. And here I'm just putting basic ODE topics, not 473 topics yet. So next lecture we'll go over the 473 stuff. So direction fields, you should know how to sketch, solving first order equations. Should know some modeling. So you don't have to be experts in modeling, but you should know how to model some things. So in ODE, we learned how to model first and second order equations. So you should know how to do that sort of stuff. And we'll do other more complex modeling, but you should have a feel for what modeling a system is like. And we'll go over that today. Systems of first order equations. So you should know how to reduce a higher order equation to a system of first order equations. Which you should have done in ODEs as well. And we'll talk a little bit about non-autonomous ODEs. So anything else I should add from that?
No, everybody here taking linear algebra?
No.
No, okay. You're gonna be
Well,
project, no.
I guess we won't need
We won't need a
like
lot.
too much.
No,
Yeah.
of course, it's
Yeah.
always helpful if you take
Right.
a course.
Plus, they had some linear algebra from ODEs as well.
From ODEs, that'll probably be.
Yeah, I mean, as far as I know, I can do eigenvalues and eigenvectors
Yeah.
and stuff like that.
Yeah, so
Okay.
you should be okay.
Yeah, you're in good shape.
So these are the topics that we should know for ODEs. And for linear, you should know these. So you should know matrix operations. So
Spell
just,
check, spell check.
oh, what, operations?
Too many Ps.
Ah, operations, there we go. Taking the determinant. That's of course important in looking for eigenvalues and eigenvectors. And also, you should probably know something about linear independence / dependence. Is there anything else we should add in there?
No, something might come up, but we can.
Yeah, so we can always do that. But I mean, if you're okay with the basics, then you should be able to follow all the topics for the most part. So let's now do some examples. Let me see something about non-autonomous ODEs first, and then we'll do some examples with modeling that uses a lot of the topics that are listed on the board. So let's say we have a non-autonomous ODE, a first order non-autonomous ODE. So x dot equals, say, x plus t. And here I'm going to use this notation for the first derivative with respect to time of x. So if you see any dots, that's a first derivative, double dot is a second derivative, etc. So we usually use this notation in dynamical systems. So let's say we have this non-autonomous ODE. Can we change it into a system of autonomous ODEs? That's what we want to think about. So since I'm asking the question, of course we can change it, but how can we change it? What can we do to do that?
I think add a dimension.
So let's think of this, right? So this is what makes it non-autonomous, that time factor in there, right? So since we have this, can't we write this? So let's write y dot equal 1. Now if we let y dot equal 1, then we can write x dot as x plus y. Right? So that means we can change any non-autonomous ODE into a system of autonomous ODEs.
By adding another equation, by adding another, in other words, time becomes that other dimension, consistent with modern views of physics. Time is dimension.
Right. So we're going to develop the theory for autonomous ODEs because we can make this sort of conversion. So that's why we won't be talking about non-autonomous ODEs, since we can very easily make this conversion. So all the theory is going to be based on autonomous ODEs. So that's the only thing I want to say about that. So now let's do a little bit of modeling. So let's take this example. Let's say we have, and this is a very standard ODE example from 222. Let's say we have a tank, and it's filled with 100 liters of, say, water. So we have some sort of tank, it's filled with 100 liters of water, and we have an incoming mixture. So we have a mixture going into the tank, and let's say that mixture is a mixture of water and salt. So we have a salt water mixture going into a tank of 100 liters of fresh water. So I want this rate to be 300 liters per hour. So the mixture is entering the tank at 300 liters per hour. And the concentration of that saltwater mixture is 1/100 grams of salt per liter of mixture. So 1 gram of salt every 100 liters of mixture. So that's the concentration that's going in. And we're also pumping this liquid out. So this mixture that's flowing in is flowing into here, and then this is coming out at the same rate that the mixture is going in. So what rate is that going to be then? So it's going to be just 300, right? Except there's a little difference here. So we don't have this concentration anymore. So now we have to think about what's the concentration of the mixture coming out. So let's first do this. Let's denote the amount of salt in the tank at any time to be x. So let x be the amount of salt.
Yeah, this looks like a standard 222 problem.
Yeah, pretty much. So let x be the amount of salt at any given time t. So we have our variables now. So what is the concentration going to be, do you think, of the water or the mixture that's coming out?
complete mixing. right?
Yes, complete mixing, yeah. Yeah. So very, very simple 222 problem, nothing crazy happening.
What's the question?
So what do we think is going to be the concentration of salt in the mixture that's coming out?
As a function
Of the
time.
tank. Right. But it doesn't have to be explicitly a function of time.
It's going to be X over the total amount of water.
Right. So the concentration here is going to be, so there's X amount of salt in the tank at any given time. So that means the concentration here is going to be X over the amount of mixture in the tank, which is 100 liters all the time. So it's always 100 liters because whatever's coming in is, so something is coming in at a rate and this mixture is going out at the same rate. So it's always going to be 100 liters. So that means the thing coming out is going to be X over 100 grams per liter. So X amount of salt over 100 liters of the mixture. So that way we can figure out what the concentration is that's coming out of the tank. So that's one of the things that we should be able to do when we model. We kind of look at what information we have and see what information we need and then fill in the gaps from the information that we already have. So this is going to be the concentration coming out. So now let's try to model this process where we want an ODE of the amount of salt in the tank at any given time, T. So how are we going to do that? So since something is coming out and something is coming in and coming out, what sort of problem is this going to be? What do we think of when we think of something changing over time?
First order, ODE.
Okay, but I mean more generally, what do we
And
think
a
of?
balance of something.
Rate in, rate out.
So we think of rates, right? So we can think of this in terms of rates. So let's break it down in terms of the rates and then figure out what's going on. So we have the rate in here. So rate in is what? So we want the rate in of the salt. So how much salt is going in per hour?
3 grams.
So it's going to be 3 grams per hour. So that's the rate in per hour. So that's the rate in, right? Now what's the rate out?
Three X over.
So it's going to be 3x grams per hour, right? Now we have the rate in, rate out, so what do you think that's going to give us? Or what are we looking for in this?
Our ODE.
Okay, but what are we looking for in the tank?
Be the rate of change.
So we want the rate of change of the salt, right? Of salt in the tank. So what do we denote that as? So or what is that?
Total rate.
But what do we write it like?
Rate.
At the time derivative?
Yeah, so it's going to be dx dt, let's say. Right? So we're going to denote it as x dot. So that's the rate of change of salt. Now the rate of change of salt is going to be just the rate in minus the rate out, right? So that means x dot is going to equal 3 minus 3x, right? So that gives us a first order ODE that governs this process. So here we modeled something using a first order ODE. So now we want to be able to solve it, of course. So we can fairly easily solve this. What do we do for this? So what's the easiest method that we can use for any sort of ODE? Separation, right? So that means we're just going to have an integral of dx over 3 minus 3x is going to be integral of dt. And then that's going to give us, so if we take the 1/3 out, that's going to be a negative ln 1 minus x. So 1/3 negative 1/3 ln of 1 minus x. So we get that equals t. So let's just make sure I didn't make a mistake. So if we take the derivative of that, that's going to be 1 over 1 minus x, and we get a negative out, and then we have the 1/3. And that's going to be t plus c, right? Let's call it c naught for now. So then we're going to just distribute, and we get ln of 1 minus x equals negative 3t plus, let's call it some other constant, so c1. And that's going to give us 1 minus x is going to equal, say, k, another constant, e to the negative 3t. And that means x is going to equal 1 minus k e to the negative 3t. So that's the simplest way to solve it.
Just a point here. In that the initial part of the calculation, where you're looking at the log of 1 minus x, that's sort of problematical, right? Because if x is bigger than 1, I mean, if the log, if that becomes a negative quantity, it should actually be the absolute value of
That's true,
what
yeah.
I'm
It
saying.
should be
What's another way of getting that answer without separation? It's a first order linear equation. Inhomogeneous, it's x dot plus x equal 3, right, or 3x equal 3. So you can find the homogeneous solution, which is the k e to the minus 3t bit, and then look for a particular solution by the method of undetermined coefficients. Stick a constant, and you get the same answer, but that's an alternative way of doing it. It avoids dealing with the log.
That's true, yeah. So yeah, there are a few ways of doing this, but I mean we can use separation for this. So then we have this, and let's just sketch the direction field for this. So in 473 we usually do the vector field, but since we're reviewing 222, let's just sketch the direction field and see if we remember how to do that. So we're going to take this and sketch that direction field. So what's the first thing we do when we sketch a direction field?
We find when the slope is 0.
Hmm?
We find when the slope changes.
Okay. So when is the slope going to be 0 for this case?
When x is 1.
So when x is 1, it's going to, the slope is going to be 0. So what do we call that?
No one?
Not too complicated yet. But like, what's the 222 definition we use for that? So it's the equilibrium solution, right? Or the fixed point of this system. And now we want to sketch what happens when x is greater than 1 and less than 1. So what happens when x is greater than 1 to this? what are the slopes like? So it's going to be negative. So it's going to be something like this. So we have negative slopes up here, and how about on the bottom? So we're going to have positive slopes on the bottom for x less than 1. And we can use dfield to do all this sketching for us, but we should know how to do some of these things. So that's just dealing with simple first order ODE. So although we get a very simple equation, it can model a fairly interesting process. So now let's try to model something using a second order ODE.
Another nice thing about that is that without really doing any calculation, it gives you a good idea of what the trajectories are. Sort of asymptote from above downward to x equal 1 and from below. Except when x equals 0, then it just stays there.
So you can get plenty of information
No,
without
sorry,
even...
not when x equals 0.
X
Stays there
equals
when
1,
x equals
yeah.
1.
So you can get plenty of information without actually solving the ODE. So that's the idea for a lot of the equations we're going to look at. We don't have the tools to solve it explicitly sometimes, but we can use some of our analysis tools to see what's going on in that ODE without solving it explicitly.
It's the qualitative point of view versus the quantitative, where without being able to write down exactly what the solutions are, you can determine what they do without writing down formulas necessary for them.
So that's why we got so many pretty pictures in dynamical systems. So now let's do a second order problem, a second order ODE problem. So does anyone want to guess what type of problem I'm going to do?
Simple harmonic oscillator.
Okay, what type? What is it?
Show this.
What physical problem do you think?
Spring problem.
Okay, a mass on a spring with a viscous damper. So I actually gave my ODE students, so Gary took this quiz. I gave them this quiz when I was teaching ODE last semester, but perhaps it was a little too difficult to give at that time. But let's do it here, because we're in.
Yes, what's that?
Yeah, exactly. All right, so say, let me actually draw this. Forget about writing it down. Let me draw this thing, and that'll give us a better picture. So say we have a 32-pound mass, and it's on a weightless spring, so we're not considering the weight of the spring. And let's say that this is a distance 4 feet from its natural length. So the mass stretches it under gravity a distance 4 feet from its natural length. And let's say that we have a viscous damper such that the terminal velocity of this, if it's on free fall through this viscous damper, is going to be 8 feet per second. So terminal velocity is going to be 8 feet per second for this.
So we usually think of it as immersed in a tub of oil or something like that.
I guess, but it's a pretty big thing. We probably need a pretty big tub for this.
Well, it depends on the material. If
That's
it's
true,
gold,
yeah,
it doesn't
yeah.
have to be that big.
That's a good point,
32 pounds.
Yeah, okay, so there's some sort of fluid. So we have this sort of setup. So what do you think the first thing we should figure out for this? So how do we solve this sort of problem, I guess?
Could use the stretch distance to find the spring constant.
Okay, we can do that, but what do we want to do for whenever we have a mass that's in motion?
Set up a system or an equation in motion.
Okay, but I guess before that, what do we do in physics?
Free body diagram.
Free body diagram. So we want to draw a free body diagram of this. Let's see what all the forces are on this. So we're going to look at all these sort of forces. So let's say it's stretched. So what do we think this is going to be then? Let's say one of the forces, or give me one of the forces.
Gravity.
Okay. But I mean, okay, so what does gravity do?
Pulls the mass.
Okay, so it pulls the mass. So the gravity is instrumental in pulling this down from its natural length, right?
Yes.
So it doesn't really play a part in the motion of it, though. That's the thing,
Okay.
right?
So that would be an applied force pulling it down?
So we're not going to put an external force on it, but there is a force when it's moving, right? But let's think of maybe the spring constant first, since Lucas mentioned it. So what are we going to do for that spring constant force? What does it look like?
So implicitly here, you're measuring everything from the equilibrium position of the thing. That's why gravity does not have any effect.
Mhm. So what do we think we're going to use for, or what does that spring constant force, the force from the spring look like?
You can usually write it as like KX.
It's a linear spring.
So let's say, yeah, it's a linear spring, that's important. So let's call it Fs, so that we can write as Kx.
Here I thought we were working with nonlinear springs.
We'll show you some problems now.
Oh yeah, we'll do some non-linear springs as well. So let's say the force that's pulling it back is Kx. So what else is there though?
The damping?
Hmm?
The damping?
Okay, yeah, there's damping. So how do we figure out what that is? How do we figure out what the damping constant or damping coefficient is going to be?
Based on the information that determines
Yeah,
velocity.
based on.
From the terminal of velocity?
Okay, so what do we do? What is terminal velocity?
Is it max speed that was traveled?
Okay, so let's draw a free body diagram for that too. So let's say this thing is falling, right? And it hits terminal velocity. So then, what force does it have pulling it down?
Gravity?
So this is just its weight, right? So mg. But what does it mean when it's at terminal velocity?
That means that the friction is equal to the gravitational force?
Yep. So there's no. So the forces are equal on it. So it's not accelerating, right? So let's call this Ft. So that's going to be m equal to mg. So there isn't going to be any sort of force on it. So then how do we figure out that the constant for the damping?
Well, you have to assume a certain kind of damping. You have to assume that the damping is proportional.
Yes, yeah,
to the-
absolutely. So nothing complicated is happening, it's just very simple damping. So what do we remember, or let's do this, do we remember what the general equation for a mass on a spring looks like?
can't you find a, from the total energy of the system, like that?
We don't have to really use energy here, so we have enough information to
There's a problem.
to solve
because
it
you don't
using
have-
force.
Energy is decreasing. This is a dissipative system because of the damage.
Right.
Okay?
Oh, yeah, so it's not counted.
Base, you can use energy calculations, but not conservation of energy
Right.
principles.
So let's write down what the general equation for this is. So it's mx double dot plus, say, gamma x dot
Yeah, what the
Plus-
gamma?
kx equals 0, right? So you want to find this gamma. So over here, let's think about what's happening with this. So we know that mg is going to equal, so this is going to equal 32 pounds. But how else can we write this force? So we wrote it on the board. So what is that force?
Gamma times the velocity.
So that's gamma times, here it's going to be terminal velocity, because we're looking at the terminal velocity system. So what's that going to be? So that's just 8 gamma, right?
It's a good example, the numbers come out nice.
Yeah, well, I always make examples where numbers come out nice.
I tried also.
Okay, so that's going to be 8 gamma, right? So from here, we can find out what gamma is, because we have that already. So we have that it's 32 pounds. So what is gamma in that case? So it's going to be 4, right?
32 divided by-
So it's going to be 4, what? What's the units on it? That's,
Feet per second times
so yeah, this is feet per second here. And we need this to be a force, so we need another per second. We need pounds, so it's going to be pounds per second, right? So that's going to give us, or sorry, not pounds per second,
Pounds times second.
pounds, what is it?
Wouldn't it be like pounds times second per foot?
Yeah, so what is
We used
pounds?
to call those slugs.
Or what is slugs, I guess? Yeah, whatever. So, okay, it would be slugs per second. So whatever that is in English units. So it's going to be that. So I guess we can write down slugs per second, right? So yeah, if we think of pounds, this is pounds. So this is slugs, and this is meters per second squared.
Should we use feet per second?
Oh yeah, feet per second squared. So yeah, this is, okay, let's see. So this is, the whole thing is pounds per second squared. And this is going to be feet per second squared. So this, or sorry, this is pounds. So this is going to be, let's see, pounds times second squared over feet, right? So it's going to be that. And then we're going to use that and figure out what that is then. So we need pounds here. This is feet per second. So we need a per second here. So it's going to be pounds times seconds over feet. So that's what it is. So if we want this in terms of pounds, this is pounds times second over feet. But this is why mathematician is non-dimensionalized, so we don't have to deal with these units.
Yeah, sure, units are the worst part.
Well, that's why we're mathematicians and not physicists, I guess. Okay, so we found what gamma is then. So we have that. So let's see how I want to put this. So if we're stretching a spring, we have a spring constant going back, and that's also the force that, so it's going to want to pull it back, and we also have, so if we let it go, we have this gamma acting on it as well. So let's say Ft is going to be gamma x dot. Or I don't want to say Ft, Fd, the force of the damper. And since it's moving up, we also have the force from acceleration itself. So we're going to write that as just, let's see, F A, let's say, is going to be the force from the acceleration, so mx double dot. So we're going to have force from that acceleration there. And we have this being the sum of the forces, so we're going to sum up all the forces and see what we got. Or I guess negative F. So then we know that we're going to sum up all of these, so we're going to end up getting our original equation here. So if we sum up all the forces, we're going to get this back, and we want to plug in the values that we found, so our gamma and our k value. So we didn't find k yet. How do we find k? So we want to find the spring constant in a similar manner to this.
From the first picture that we do.
Okay, so
That one.
So let me erase this and then let's find k here. So let's draw it for k. So let's say this is mg again. This is going to be what? So let's say it's in equilibrium right now.
It's probably going to be force.
So it's kx, right? So we have that. So that means, and since it's in equilibrium, we're going to have that kx, so what's x in this case?
4.
So this is 4k is going to equal 32 pounds. So that way we get k. So what's k? So k is going to be 8. So we have that. So we found everything we need. So here, what is this equation going to become? So we didn't explicitly find m, but what do we have for that?
32.
So what is m? So it's going to be force over acceleration, right? So m equals force over gravity. We know the force is 32 pounds. What's the gravity in English units? No, that's SI. Or that's approximately 10 in SI, but that's SI as well.
That's like meters.
Yeah.
Be sure if it Here.
I'm not sure it's how.
So there's a reason I chose 32 pounds.
That's 32.
32 feet per second squared, yeah. So we get that. So that's going to give us 1 pounds times second squared over feet,
That's slow.
which is slows. So then we can write down our model for this. So we're going to have x double dot plus the gamma, which is 4x dot, plus from the k, which is going to give us 8x equals 0. So we get that. So we model it basically using Newton's laws. So we end up with a second order ODE, which we can solve. But let's not solve it. Let's break it down, or let's reduce it into a system of first order ODEs. So we can use some of the techniques that we're going to use in this course. So how do we reduce this into a system of first order ODEs?
Introduce a new variable.
Okay. What variable do you want to introduce?
Y or
Or v.
v, yeah. Okay.
So what do you want to?
You can let v equal x dot.
So let v equals x. Let v equal x dot, right?
So I guess v double, well, yeah. So v double, well, v dot is equal to x double dot.
So v dot does equal x double dot. So we can plug this in here. So that equation becomes v dot plus 4v plus 8x, right? Equals 0. So since we have this, we have a system of first order ODEs where the first equation is x dot equals v, and the second equation is v dot equals negative 4v plus or minus 8x. So that way we can break it down into a system of first order ODEs.
We have found the roots.
Hmm?
Like,
Yeah. So you can solve this, right? It's very easy to solve. We could just find the characteristic polynomial and then find the roots of that, and we can solve it. But we know how to solve it. But let's use some of the techniques that we're going to use in this class for problems where we don't know how to solve it, or we don't have a method to solve it explicitly. So that's why we want to do this. So if we break it down into a system of first order ODEs, we can use dynamical systems analysis to analyze the system that we have. So we don't have to solve it, but we can get a lot of information out of it without even solving it. So we do this. Now what do we usually do in dynamical systems to analyze these sort of problems?
Say back to.
Okay, but before we do that, so let me see what you guys say, and then I'll say.
Okay, find a fixed point.
Okay, yeah, we can find a fixed point. Well, let's find a fixed point next time, since next time we'll do more of the 473 review. So in ODEs, we didn't really find fixed points, but we can find the fixed points for this. It's not too difficult to find these fixed points. So yeah, let's go ahead and see which. You tell me what the fixed points are.
Okay, when v equals 0,
Uh-huh.
so x had to be 0 too.
Yep, so the fixed point is 0, 0. So it's a very easy fixed point, but let's not bother with that this time. Let's do that in next class for the 473 review.
You want to write it as a matrix equation?
So let's write it as a matrix equation, and let's do some stuff that we did in 222, like finding eigenvalues and eigenvectors. So we can write it like this. So we have x dot and v dot. So what's that going to equal if we write it down as a matrix equation?
1, 0, negative 4, negative 8.
So it won't be 1,
Or it'll be,
it'll be the other way around.
Yeah, 0, yeah.
0, right?
Yeah.
So it'll be 0 there, negative 8 there. It's going to be 1 there and negative 4 there, times xv, right? So we can write it like this. So we can write it like a matrix equation, and then we can find the eigenvalues and eigenvectors.
Don't erase that yet. I just
Oh,
want
yeah,
to throw
sure.
something at you. This is a very simplified version of modeling this physical problem. But the real physical problem, if you think about it, it's fun to do, is quite a bit more complicated than that. Why? First of all, there's another force on the weight, the buoyant force for the liquid. Secondly, what happens when the thing is not totally submerged? It's partially in the liquid, partially without. If you throw in all of those things, it becomes a slightly more difficult equation, but it's still doable. I mean, usually what you do is, when you take a model, you think about all of the physical things, modeling all the physical things, and then maybe shaving some of them off, the ones that are maybe not that important in certain ways, but you have to be very careful. In this case, not so much. This is a linear differential equation, so making these adjustments. But when the differential equations are nonlinear, even if the nonlinearities are extraordinarily small, they can cause chaos. Chaos lies in the nonlinearities. Anyway, just all right.
So yeah, we want to find the eigenvalues and eigenvectors for this. So how do we do that? So how do we find the eigenvalues?
Set the determinant equal to 0.
Okay, determinant of what?
Subtract.
We'll subtract the lambda.
Yeah.
Okay, so let's think of what the eigenvalue problem is, right? So what is an eigenvalue problem for matrices?
The matrix minus I times lambda. Right?
So we want to solve this this problem. So we have A minus lambda I, and then what? What do we have?
You guys said they make the determinant equal 0.
Okay, so we do want that determinant to equal 0. So, okay, let's go ahead and do that first, and then we'll think about what the eigenvalue problem is. So we do want this determinant to equal 0 to find the eigenvalues lambda. But we'll see why we're doing that. So we want to take this determinant to be 0, so that's going to be what? So this is negative lambda.
1.
Minus 8 there, 1, and minus 4 minus lambda, right? So what's the determinant of that going to be?
Lambda squared plus 4 lambda plus 8.
Yep. And we want to set that equal to 0, right? So now, what's lambda going to be in this case? So it looks like we're going to have to use the quadratic formula. Unless anyone can see a way of factoring that easily. But, yeah. So let's use a quadratic formula. So what is the quadratic formula?
Minus 4
Okay, so yeah, so minus 4
plus or minus
plus minus.
square root of 4 squared
So 16.
minus 4ac, which is
So
4, 8.
So what's 4 times 8?
16.
No,
No,
32. That's all right. Over 2, right? So over 2a. But yeah. So we got this. So then 16 minus 32 is what?
Negative.
So negative 16. So then what do we get from the radical negative 16?
Imaginary
2i.
Huh?
4i.
4i, right? So we're going to have negative 4 plus or minus 4i. So that's going to cancel out with the 2. So it's going to be negative 2 plus or minus 2i, right? So those are the two eigenvalues for the problem.
Quick question, can anybody prove the quadratic formula?
Ah, how do you prove the quadratic formula? Gary, you better know this. We did this in T22.
I must have been late that time.
Or sleeping.
Complete the square.
Yeah.
Yeah.
Complete the square of the quadratic. Pops right out.
Oh wait, I didn't do it in class. I did it during a review session. That's right. Yeah.
And he didn't need a review.
He didn't need a review. Yeah.
Completely.
Okay, so we get this as our eigenvalue. Now we want to find our eigenvectors. But let's now think of what sort of problem the eigenvalue problem is. So do we remember what an eigenvalue problem is? It's a really interesting type of problem. So let's say for differential equations, do we remember what it is? Or what one type of eigenvalue problem is? So I'll tell you for matrix equations, we want to solve a problem like this. AX equals lambda x. And there are these special, I guess, constants or coefficients of x, scalars, yeah, where this equation can be solved for some particular x. So this is the type of problem that we want to solve.
Different from zero.
Different from zero, yeah. We're not interested in zero. We don't want trivial solutions. So there, I mean, obviously zero would work, but different from zero. So that's the type of problem we want to solve. So that's why we take the determinant of a minus lambda I to equal 0 to find our eigenvalues. Now, to find our eigenvectors, what do? So what is another way of writing this? So we can write it like this, right? A minus lambda I times the vector x equals what? So it equals 0, right? We want to find the vectors x such that this will equal 0. So that's the problem that we want to solve. So that's how we find our eigenvectors. So let's call the first eigenvector just x negative. So here we're going to use the negative branch. So how do we find that? Before we do this, let me just write it. So what equation are we solving?
We gotta plug that value as a lambda. And then
Right. So we have our A minus lambda I matrix here, but it's written as a determinant, but that's okay. So we can take this matrix, plug in one of our eigenvalues, and then see what x makes it 0, makes that multiplication 0. So we're going to do that. So our A minus lambda I is this. So let's use a negative branch. So that's going to be 2 plus 2i. And we still have a negative 8 on the bottom. We have a 1 on top, and on the bottom here is going to be, so that's going to be negative 2 plus 2i times x, let's call it x negative, equals 0. So that's the problem we want to solve. So what does the trick? So when we look for this vector here, we need to make sure that the multiplication of any row times this vector is going to have to be 0, right? So let's look at the first row. This first row times this vector, how is that going to be 0? What do we need that vector to be?
1 and 2 plus, or negative 2 minus 2i.
Okay. So from that first row, we get this. It's going to be 1 and negative 2 minus 2i, right? So that would make that multiplication 0. Of course, we have to also make sure that this row times this vector is going to be 0 as well. But it will be. So if you actually do the multiplication out, you get this times that. So let's actually do it. But if you do the multiplication, you should see that this times that should give you 8. So then you get negative 8 plus 8, and it would be 0. So this clearly makes this multiplication 0. Let's just make sure that this
For
doesn't
those who
change.
know linear algebra, why is that true without the calculation? The determinant is equal to 0, which means the first and second row are linearly dependent. So the second equation is just a multiple of the first.
Right.
But
So it's always going to be that case, but just to make sure you don't make a mistake, you better make sure that it is that case.
check your answer.
So, yeah, if you have that first row gives you a 0, you better get that the second one also gives you 0, or else you did something wrong. So if you see here, we have negative 2 plus 2i times negative 2 minus 2i. So we have negative 2, that's going to be 4. We have that the other i's, the 4 i's, will cancel. And then we have 2i minus 2i, so that's plus 4, so that's 8. So it works. So this is going to be one of our eigenvectors. So how do we find the other eigenvector?
We plug the other value in.
So we're going to plug the other value in. Let's see what that gives us. So this is x positive, let's say. So this is going to be, if we plug in negative 2 plus 2i, we get 2 minus 2i here, negative 8 here, 1 here, and negative 2 minus 2i here. So we get that. And let's just make sure it's correct. That's going to be plus 7, that's minus, yeah. So we got this, and we want to solve this. So which x positive does the trick? So we're going to use the same sort of thing that we did before.
We do 1 and then negative 1 times 2 minus 2i, so negative 2i plus 2i.
Yeah, negative 2 plus 2i, right? So that'll do it. And if we multiply this with this again, we get that it's 8, but we already did that. So any question? Yeah, go ahead.
How can you tell in advance that that's going to be the answer without doing that second calculation? Once I saw x minus, I knew exactly what x plus is going to be. Why?
They're conjugates.
Complex conjugate. So you know that the eigenvalues, because it's a real polynomial, are complex conjugates if they're not real themselves, which means that the eigenvectors are also complex conjugates. So I think the complex conjugate of that eigenvector, it gives me that.
Now, if you don't have complex conjugates, then you do have to go through this and do it for each eigenvector. But this is how you would do it, basically. And we can do a lot of analysis on this, but that's all the linear algebra and ODEs that we had done in 222. So next time we'll do we'll do more of the 473 stuff. So we'll do some more interesting problems, and we'll do more dynamical systems analysis rather than just the usual ODE things. So, anything that you want to add?
No, yeah, sort of in reference to that, so you take this system that we just looked at, suppose we want to plot the trajectories, right, in the XV, whatever plane it is. How can we use that information without finding exactly what the solution is? It's easy to find the solution, the general solution, right? It's just this second order constant coefficient homogeneous equation, use the characteristic polynomial, and you get the exponential solutions. You know the drill. But what do those solutions look like? How can you represent, maybe not just one of them, but characterize maybe a whole, sort of a whole array of solutions as they kind of work themselves out in that plane. And that'll give us a lot of information, basically just by seeing how the solutions behave rather than knowing exactly what the equation is for each of those trajectories.
So for those of you who haven't seen dynamical systems, it's going to be very similar to the direction fields, except now we're in 2D for the second order problem. So we're going to use something called a phase plane for that.
So you're plotting x as a function of t and y as a function of t. So you have these parametric curves that represent the trajectories in the phase plane. It's called the phase plane. Get all those interesting pictures.
So yeah, that's all the review I was thinking of doing for today. So next week, I'll give you guys a very simple quiz with some of these topics. So I won't make you model these things because that would take too long, but I'll just test you on some of the basic topics, just so I see that you can do the computations. Also, if I have listed on here the section numbers, just make sure that you skim through it, just so you know what's coming up.
Stroke right?
So yeah, and stroke
Yeah.
hats. So yeah, I'll
Start
use-
reading, if you haven't taken 473, start reading Strogatz. It's a good read.
It's a very
One of
good
the
read.
best
Yeah.
textbooks I've used,
Yep.
actually.
Absolutely.
I mean, it reads like a novel. So.
Yeah.
Right.
Yeah, exactly.
Very understandable, look at the problems, you can sort of get yourself up to speed
Right.
rather very quickly.
So if you don't have Strogatz, it's a good idea to get it, and it's a good idea to just go through the sections before class as well. So next week we'll do the dynamical systems review, fixed points, phase planes, etc., and we'll just have a little quiz beforehand. So any questions or? So I guess that's the lesson.
Seems like a nice class. Everybody's interested. You can't say that, you rarely can say that, you never can say that in a regular
Well, it's
class,
nice to have
that
it.
everybody is interested.
That's true, yeah.
Virtually. This is a good size room.
Yeah, yeah.
It's like this, plenty of boards.
Yeah.
I like this one. It's probably better.
Right.
It's very comfortable.
I was hoping you were.
And Conley said that no one's here on Tuesdays from
Yeah.
4 to 6, so. So yeah, I guess I'll update you guys on the office hours and stuff like that.